my name is Professor Rad, and this is Precalc video 3.9, graphing tangent and cotangent. In the previous two videos, we've been working to graph sine functions, cosine functions, secant and cosecant. So now we get to round out the trigonometric family by graphing tangent and cotangent. So if you haven't watched those videos yet, I recommend that you watch those first because we're going to skip through, or going to depend on some foundational reasoning to graph these, so we can graph them a little bit more quickly. So we've been using the unit circle to help us graph our trig functions. So we're going to do that for tangent and cotangent as well. So for tangent, it's going to be y over x. So this is the ratio that we're going to be graphing in terms of these angles here. So if I look at tangent of 0, so 0 is going to be 0 over 1, because that's our y value over our x value, and that's going to give us 0. So at an angle of 0, the tangent value will be 0. Then when I go to pi halves, I'm going to get 1 over 0, and that's undefined, so that doesn't help us. When I get to pi, now we're going to have 0 over a negative 1, which is still 0. So at pi, we're going to be 0. And then at 3 pi halves, we're at 0, negative 1. So y over x is negative 1 over 0. We have an issue. And then at 2 pi, we're back to 0 over 1. So we're back to 0. So it looks like for tangent, we're getting x-intercepts. Oh, there should be a negative 2 pi, goodness. We're getting our x-intercepts at integer multiples of pi. This is different from the other graphs that we've had, because in the other graphs we had like some non-x-intercepts for us to graph and see what's going on. So we're gonna need some more here to help us graph. So first thing, just like with secant and cosecant, the places where we are undefined, so the places where we have 1 or negative 1 over 0, that's going to correspond to an asymptote on our graph. So we're going to have asymptotes here at pi halves, 3 pi halves, 5 pi halves, and so on. So all the odd pi halves. And then same thing with the negative side. Now with secant and cosecant, we had kind of these explosions of the sine and cosine functions. So we had these u's that went up and went down. We're not really getting that here because we've got these values where we do equal 0. And how would we be able to tell if we explode up or explode down? Because we're kind of like a quotient of those two squiggly curves, not the reciprocal of them. So I don't think the explosion analogy is a good way to think about this one. So instead, let's see if we can find some other values to graph. So there is a nice value for tangent. If I have tangent of, say, 45 degrees, which is pi fourths, the x and the y values are the same. They're root 2 over 2. So that when I take the ratio of them, root 2 over 2 over itself, is going to give me 1. So I can graph this function, or this point rather, when I have a theta of pi quarters, which is half of a half. So we're here. I get a y value of 1. If I go over here, I have a negative x and a positive y. So I'm going to get a positive over a negative, and that's going to correspond to a negative 1 here at 3 pi over 4. With 4, this is going to give me 5 pi over 4. I now have a negative x and a negative y. So I have a negative over a negative, which is going to give me a positive 1. And then when I go into the fourth quadrant here, I've got a positive x, but a negative y. So I'm going to get a negative root 2 over 2 over a positive root 2 over 2, which is going to give me a negative 1. So this pattern of negative ones and positive ones is going to repeat. So I'm going to have a -1 here, +1, -1, +1, and so on. So now we have some nice points that we can be graphing. And we know from our work about reciprocals that as we get closer to the asymptote, it's going to kind of explode up or explode down. So the way that we're going to connect these points, it's not the same shimmy that the cubing function has. So x cubed has that little shimmy through the origin. So tangent also does a shimmy. It's strictly speaking not the same shimmy, but it's close enough. Okay, so we're going to kind of shimmy up and over this way, down and over that way. And that's how we're going to connect each of our points. So we can shimmy up this way and that way, and so on. And as with all of our other trig functions so far, tangent is going to be periodic. So it's going to be repeating itself throughout. All right, so if you're up for a bit of a challenge, here's my recommendation. Pause the video here and see if you can use a same or similar technique to graph cotangent. If you're like, can we work through that one more time? Let's graph cotangent together. So if you want to try graphing cotangent on your own and check your results, pause the video here. Otherwise, spoilers ahead. So when I go to graph cotangent, now the ratio is x over y. So I'm going to have asymptotes at different places because now if the y value is 0, that's where I'm going to have an issue. Whereas with tangent, when I had an x value of 0, that's where I had an issue. So let's see when the y value is 0. So the y value is 0 here at 0, and it's 0 here at pi, 2 pi, 3 pi, 4 pi, 5 pi, so on. So the cotangent function is going to have asymptotes at the pi's. So here at 0, here at pi, 2 pi, negative pi, and negative 2 pi. Then, when we have the ratio of like 0 over 1, so now we have like an x value here of 0 and a y value of 1. That's where we're going to get our x-intercepts. So cotangent is going to be 0 at pi halves because we'll have 0 over 1. It'll be 0 at 3 pi halves because we'll have 0 over negative 1. And then if I had moved clockwise, I'd get an intercept here at negative pi halves and negative 3 pi halves. Now here's where something kind of strange is going to happen. So when you have the same like x and y values, when it simplifies to either 1 or negative 1, like when we had root 2 over 2, root 2 over 2, or maybe here when we had root 2 over 2, negative root 2 over 2, it doesn't matter whether you had the x over the y or the y over the x. You'll get the same value, right? So what that means is, excuse me, for pi fourths, cotangent is going to be a positive 1. So for pi fourths, cotangent is going to be a positive 1, just like tangent was. For 3 pi fourths, we're going to have a negative root 2 over 2, because that's our x value, over a positive root 2 over 2, because that's our y value here. So this will simplify to negative 1. So at 3 pi fourths, we're going to be at negative 1, just like we were for tangent. So tangent and cotangent are going to equal 1 and negative 1 at the same places. So we're going to have this fluctuating 1, negative 1 business happening again. And then to connect the points, we're going to connect them similarly to our tangent graph, but now this time they're going to be going in the opposite direction. So whereas tangent shimmied up, notice that cotangent, because of the shifting of the intercepts and of the asymptotes, is now going to be shifting down, or shimmying down rather. So we're going to get this shape for cotangent. So if you pause the video to try and graph cotangent on your own, how did you do? Did you do all right with it? Okay, so as we did with our previous videos, with secant, cosecant, sine, and cosine, we looked at properties of those functions after we graphed them. So let's do the same thing for these. Let's do some properties of tangent and cotangent. So let's look at properties of tangent first. Alrighty, so let's begin looking at some of the properties that tangent has. So because tangent has asymptotes, just like with secant and cosecant, we're going to have to account for those asymptotes when we state the domain. So tangent's asymptotes happen at the odd pi over 2. So the domain is going to be all of the thetas, so that theta does not equal k pi over 2, where k is an odd integer. So we're going to have problem spots there at the k pi over 2. We can also go ahead and write that in for our asymptotes now while we're thinking about it. So the vertical asymptotes of tangent are going to be wherever we have odd k pi over 2. So we have theta equals, or I'm going to write x equals k pi over 2, where k is an odd integer. Next, we're going to want to state the range for the tangent function. So for the range, because we have these vertical asymptotes and these arrows, and we're connected between those asymptotes, our range is actually all real numbers. So we span from negative infinity up to positive infinity. So the range is all real numbers, or you can write that as negative infinity to positive infinity. Next, we'll want to state the period for our tangent function. So the period for sine, cosine, secant, and cosecant have all been 2 pi because we've gotten to see the whole function in the span of 2 pi. If I look at tangent, as I go from, let's go from 0 to 2 pi. So if I go from 0 to 2 pi, we have the up edge of the curve, asymptote, bottom part, top part, asymptote, bottom part. So actually from between 0 to 2 pi, I'm seeing the tangent happen twice. You can actually see this a little bit better if we look between asymptotes instead of like 0 and 2 pi. So for instance, if I look at between negative pi halves and positive pi halves, that's the piece of the tangent function that's going to keep repeating. So the period for tangent happens between negative pi halves and positive pi halves, which is only a distance of pi. So the period for tangent is pi. So it's not 2 pi. Tangent has a different period than sine, cosine, secant, and cosecant. For the x-intercepts, that's going to happen at these green points here. Those are happening at the k pi's. So the x-intercepts are going to be every k pi, 0, where k is an integer. Right, so this time we don't have to specify that k is an odd integer because it happens at each of the whole number pi's or the negative whole number pi's. All right, lastly, let's look at the symmetry of the tangent function. So our tangent function is symmetric through the origin. So for example, if I look at pi and a quarter, the y value is 1. And if I look at negative pi and a quarter, the y value is a negative 1. So we are symmetric through the origin. So that means that tangent's going to be an odd function. So tangent of negative theta is negative tangent of theta. Right. So now that we've taken the time to look at some symmetries for, or some properties for tangent, let's repeat this process for cotangent. So I'm gonna give you a moment to pause the video and use the graph of cotangent to fill in these same blanks for cotangent, and then we'll unpause and we'll go through it together. Make sure you practice it. So did you take the time to find the properties of cotangent? So I've written them over here on the side so we can use that to check. If you want to pause and check my answers with your answers, go ahead. But I'm just going to run through them. So the domain is everything that's not a k-pi, because that's when we have our asymptotes here. The range is still all real numbers. The period is still pi because each of these intervals between the asymptotes has a distance of pi, and that's when cotangent is going to repeat itself. The x integers are k-pi over 2, 0, where k is an odd integer. So at 1 pi halves, 3 pi halves, 5 pi halves, so on. Our asymptotes are at the k-pi's because that's what was forbidden from the domain. And this is something that's different from what we've seen before. So in sine and cosine, we had one odd, one even function. With secant, cosecant, we had one even, one odd. With tangent, cotangent, both odd. It's kind of odd. So if we wanted to check that, so if I look at, let's go with 3 pi fourths. If I look at, that will give me a -1. If I go to -3 pi fourths, that gives me a +1. So just like tangent, cotangent is going to be an odd function. Kind of interesting. So, so we are symmetric through the origin, and cotangent of negative theta is negative cotangent of theta, and we are an odd function. So how did you do at identifying those features of tangent and cotangent? Did you do okay? So with our other videos, we've been doing one more thing. We've been comparing to see how we can take one function and transform it into the other one. Now notice, because tangent goes up and cotangent goes down, we can't just shift. So with sine, cosine, we could shift one to get the other. With secant and cosecant, we could do the same thing. But with tangent and cotangent, we're going to have to do more than just shift. So let's give ourselves some space here on the board and think about how we might need to do that. So let's start out with cotangent and see how we can morph that into tangent. Well, just start out with cotangent of something here. So let's see, one thing that I'm going to need to do is I'm going to need to bring the x-intercepts over by amount of pi halves. So there is some shifting involved. Maybe I want to shift to the left or want to shift to the right. Either way, actually, it's going to work out, right? So if I shift this pi halves over to pi, I get my intercept. If I shift it over to the left, I get that other intercept. So we know pi halves is going to be involved in a shift. However, if I want to take this and flip it, then I'm going to be reflecting. So maybe I want to reflect over this y-axis. So that will get me my curves going up instead of coming down. So to reflect over the y-axis, we're going to need a negative theta. And then we can shift either left or right. So I'm going to choose to shift left. So I'm going to add pi halves, mostly so that I can rewrite that as cotangent of pi halves minus theta. That will equal tangent. And actually, we can shift tangent and reflect tangent in exactly the same way and get cotangent. So for example, if I were to reflect this piece, so think about this curve here being reflected. So now it's going this way. And I shift it to the left by pi halves, that will give me this piece here. So cotangent is also equal to tangent of pi halves minus theta. So it's kind of nifty. We can do this shifting to get tangent and cotangent to be the same. So that's where we're going to conclude this video today. We have one more video about graphing trig functions. We're going to be graphing sinusoidal functions. So a sinusoidal function is a transformation on sine and cosine. And we can use our typical transformation techniques to graph that. However, because our axis is indexed by pi, as in terms of pi, those transformations can be a little bit challenging. So we'll talk about some techniques to help us reduce the challenge a little bit and make it easier to graph those functions. So I'm looking forward to seeing you in that next video. In the meantime, I hope you found this video helpful in graphing tangent and cotangent, and I also hope you have a splendid day. So bye for now.